All right. So as we know how to calculate all the equivalent energies, which is the power, depending with what you are given on the internal combustion engine, we can have a part whereby they will need us to end up with the heat balance sheet. Typical questions like of this nature, where you are required to draw up the heat balance sheet. And this, in order for us to have it at the end, we need all these, the heat loss, the heat this, all these, they are needed. They comprise of what we refer to as the heat balance sheet. All right, what is it that we are referring to here on the heat balance sheet? All right, given that, let us take a consideration. The heat balance sheet is comprised of the heat that is from the fuel. So in actual sense, we have got the heat from the fuel in this case. All right, let us just do this. We have got the heat from the fuel. All right, so that is the heat from the fuel. We know that it's required. It is referred to as the fuel power, which is the one that we obtain from the mass times the heat value. So we have the fuel power, which is the heat from the fuel. And this heat now is going to be separated into branches. Which branches are we referring to? All right, it is going to be referred to this way. So we are going to have the part that is of the indicated power. All right, we have got another part that is the heat to the coolant. And also we have the heat to the exhaust gases that we have, and also the remainder part. So this is what we have. All right. So what I'm simply saying is that this is going to be separated into the indicated power, where the indicated power, remember the indicated power is the sum of the two, which is the brake power and what? The friction power. So there we have got two things that we need to consider in this case that give us, or that build up this indicated power. So the indicated power is built up of the brake power and the friction power. The friction power. So these two, they give us, or they build up the indicated power. So in actual sense, we are simply saying the indicated power is, or it is going to be given as, the indicated power is the sum of these two. That is the brake power plus the friction power. All right. So since we have formulas that are used, or that can be used to calculate the indicated power, you see that in most cases, you are the one who is to calculate the indicated power. We have good formulas to calculate the brake power. You are the one who is to calculate that brake power because they are formulas there. But you do not have the formula direct for the friction power. So it means we can manipulate from this. Therefore, it follows that if we are to make this friction power the subject, we just have to transpose the brake power to the other side. So therefore, it means the friction power, because it is the one that in most cases you are being asked. It is going to be the indicated power minus the brake power. You transpose the brake power to the other side. So it's going to be indicated power minus the brake power. So what I'm simply saying is that because the indicated power, remember there are those formulas that you can use, the Planck formula or those who use plus to find the indicated power, or whether it's the brake power, where we are using the 2 pi nt over Tn or nt over 60. We can calculate this. So they know that once they give you the information, you can calculate those ones. But the friction power, you do not have a direct formula, so you manipulate it from there. All right? So that's the power that we have. So here we have got the heat to the coolant, the heat to the coolant. And also we have got the heat to the exhaust. Remember, there are exhaust gases there. So we have got heat to exhaust. Then we have the remainder. So this is going to be the remainder of heat. So in other cases, what you're going to see is that they are going to remove up the friction power. All right. They are going to remove this. And you just remain with the brake power in most cases. All right. So the old balance sheet that we had, it uses the friction power. So now, because of this changing part, we can have the friction power added to the remainder part. All right. But I'm going to explain as it is with the brake power, the friction power, and so on. So these are the energies, these are the heat that we need out, which is the brake power, the friction power, the heat to the coolant, the heat to the exhaust, and the remainder. These, they build up our heat balance sheet. All right, so let us list them. So what you're gonna do, remember we said we've got the Q that is inside. So this is just a sketch of what you are going to need, including the friction power. So including the friction power, okay, like I said, guys, this is just a sketch. So we're gonna have the heat in, that is the heat from fuel. This is the heat from fuel, which is actually Qn. All right. So this heat, I'm not gonna mention to say it's kilojoules per second, or it's kilojoules per minute, or it's kilojoules per hour. You use it according to the units that you're given. So this table, you draw it according to the units that you are given. Draw according to the units given. According to the units given. What am I trying to say? They might ask you this way, in kilojoules per minute, meaning to say you have to use your units in kilojoules per minute. If they say kilojoules per second, you have to use kilojoules per second, which is, remember, kilojoules per second is equivalent to kilowatt. So you must be able to manipulate your units. Kilojoules per second and kilowatt is the same. But if we are given kilojoule per second and you want to find the kilojoule per minute, from a kilojoule per second is going to be kilojoule per second times 60. That is to convert to kilojoules per minute. It is, how are we given the information? So the Qin is the total heat that we have. And we know that our fuel power in this case is the heat that is in. The Qin that we're talking about, that is the fuel power. And guys, we talked about the formula for the fuel power. We said this is the mass of fuel times the calorific value, which is the heat value. So this is the one that changes our units. If it is kilojoules per second or kilojoules per minute, it means our mass is going to be mass of fuel per the unit that we're given. So this, it depends with the units given, depends with the given units. With the given units. It's on the exam. It's not going to be a fixed. I'm not going to say it's supposed to be kilojoules per, kgs per second. Do you use that according to how they're asking? They will ask you, draw this in kilojoules per minute. Then you know, okay. So if it is kilojoules per minute, it means the mass must be in kilograms per minute. That is the idea there. All right. So we shall see that with our questions. Then that's the Qn. Then the other is going to be the heat that is being transferred to, which is the flow destination. So in this case, we've got the heat flow destination. All right, the heat flow destination. The heat flow destination, that is Q out. Where is it going to? All right. So as we saw that the powers or the energies that we are given, the heat that we need will be these ones: brake power, the friction power, and so on and so on. So you're going to have the brake power, which build up Remember, they build up to give us the indicated power. So it is built up of the brake power. It is built up of what? Of the friction power. The friction power. Then from there, we saw that we're going to have the coolant to the exhaust and the remainder. So we also have the heat that will be taken to the coolant, to the exhaust. And the last one, that is the remainder now of the heat. So this remainder is by what? By difference. You are going to have this by difference. What am I trying to say by difference? Remember, we have a total in this case, which is the Qn. The Qn is the total heat, this one. This is the total heat that we have. So meaning to say, from the difference that we are having, from the difference of that, because it is the total that we have, this one, which is our fuel power, that is our total. So we subtract these, the brake power, the friction power, the coolant, the exhaust. From the fuel power, you get what? The remainder. That is how you get the remainder by difference. All right. Then the percentages, definitely you're going to need the percentages. So this will be, you're going to have your values that corresponds to each and every part to the total. Then the percentages corresponding to the brake power and so on, which is the percentage heat supplied. All right. So that is be our table. So these are the percentages. Brake power over the fuel power times 100%. The friction power over the whatever that we want. It will be what you want. The coolant over the fuel power times 100%, you get the percentage for the coolant. The exhaust over the fuel power, which is our total, times 100%, just like that. So like I said, the units, this is drawn according to the units that you are given there. So I'm not going to explain. I'm not going to write to say this is supposed to be kilojoules per minute. No. No, not like that. It depends. How are you given from the question? You work with how you're given it. But the units is simply kilojoules per given time. So this will be simply in what? In kilojoules per given unit of time, per given unit time. Is it per second? Is it per minute? Is it per hour? That you are given. All right. The percentages, definitely, they must add up to 100% if we add up everything. Okay, so that's it, guys. So how do you calculate the brake power? We talked about the formulas for that. The friction power, we said it's a remainder. I mean, the one that we subtract from what? Indicated power minus brake power. How to calculate the indicated power? We talked about that. Then Q for the exhaust, we talked about all those formulas. So all we need, guys, is to have something like this at the end. So if they do not put the friction power like this, they are going to tell you a statement, this and that percentage was taken to the remainder. So it means everything will be put to the remainder. Everything will be put to the remainder. You won't have the friction power. All right? But in this case, we are considering to have it. All right? Let us check how questions are given. So I think with this information, we can answer any question. You're going to just go back as an individual, just go back to recap at this and that, how is it given, and so forth and so forth. But I'm just going to remove this so that we can answer our questions. All right, there we are given typical questions that we might be given. Example 2, that here, the data that we have for a 4-stroke, take note. This information, the data that we are given, is for a 4-stroke. So we are given a 4-stroke single cylinder. All right, so that's a 4-stroke in this case. And it's a single cylinder, that is E is equivalent to 1 single cylinder engine tested by rope brake. Remember, by the rope brake, that is where we talk about the brake power from the 2 pi Tn over 60. All right, so this is by rope break. By rope break here. So what are we given on this part? The speed, which is the speed at 350 revolutions per minute. Then also we are given in this case, if we are to check the cylinder diameter, that is 192 millimeters, the stroke, which is 0.357. So that is the information, the data that we have on our cylinder, this and that. All right, so we are given there the diameter and the stroke length, guys. Let us just see. If you convert to meters, divide by 1,000, that will be 0.192 in meters. Then the stroke length, it will be 0.357 in meters. All right, so about the rope break information, we are given that on the net load on the rope break with a mean diameter of the wheel. So this is about the break here of the rope break, not of the cylinder here. No. So we are given the diameter, which is 1,448 millimeters. So if we convert to meters, that's if we divide by 1,000, that will be 1,448 in meters. This is our diameter. But remember, the moment you're given this, we're supposed to be talking of the what? The radius, which is diameter over 2. So that's 1,448 over 2. Remember that why am I talking about the diameter, about the radius? That is the one that we need to calculate the torque. So that will be 0.724 in meters. So from this rope break condition, we also have the radius, which is 0.724 in meters. And what else? The mass there, because this is the rope, the net load is what? 40 kilograms. So the net load, which is the mass, it's 40 kilograms. The fuel used, it's 1 kilogram, is equal to 1 kilogram during a test of 20 minutes. So we have got the mass of fuel, 1 kilogram in 20 minutes. The mass of fuel is given as, take note, 1 kilogram in 20 minutes. So from here, you can play around with this mass of fuel to the way that you want. You can have it as the mass of fuel per minute, meaning to say that will be 1 over the mass, over the time in minutes. 1 kilogram, the mass in minutes, that will be something like 0.05 kilograms per minute. Guys, you can have it the way that you want. You can have it in mass of fuel per second. If 1 minute is equivalent to 60 seconds, therefore a minute there, we divide by 60. So it will be 0.05 again. We divide by 60, that is 2 seconds. Take note. So that will be something like 1 over 1,200, because it will be like a decimal, bigger decimal there, which is 1 over 1,200 kilograms per second. Guys, we can convert this even to the mass of fuel per hour. If we know that in a minute, in an hour, actually in an hour, we've got what? 60 minutes. What about in a minute? How many hours do we have? That's 1 over 60. So that means this will be 0.05 over 1 over 60 like this, or we multiply by 60. That's another way. Simply multiply by 60. So this will give us 3, which is 3 kilograms per hour. Guys, I'm simply saying we can play around this mass that we are given in 20 minutes the way that we want. It depends with the question thereafter. What unit is needed? Is it per second? Is it per hour? Is it per minute? The unit thereafter controls our question. All right? So yeah, guys, we're just, let us just take all information. This is an exercise. This is not a question paper. So an exercise, we can do whatever that we want, guys. We just want to know, to play around these questions. The heat value is given. The heat value of fuel is what? 44,600 kilojoules per kilogram, which is fine. We have got the heat value, which is our calorific value. This one, there's no problem. Our calorific value, which is the heat value, 44,600 kilojoules per what? Per kilogram fuel. This is what we have. Then they gave us here the cooling water flow. It's 300 kilograms per hour. What is it? The mass, kilograms, the mass of cooling water. There we've got the mass of cooling water. This was the mass of fuel. There we've got the mass of water per hour. They gave us per hour, 300 kilograms per hour. Depends with the units. Maybe we're going to change the units later on. All right, but this is about the cooling water. Let's see about the same cooling water. The mass of this cooling water is this, all right, with a mean temperature rise, of the cooling water. It has a mean temperature rise of 11 degrees Celsius, meaning to say that's the change in temperature there for the cooling water. The change in temperature was 11 degrees Celsius. We are still under the cooling water. So this whole part is about the cooling water. All right. So this is for water. What else do we have? We are also given the air fuel ratio is 25:1. Air fuel ratio 25:1. So this is about air and fuel, 25:1, which is air fuel ratio. That is the mass of air to the mass of what? To the mass of fuel. I'm going to explain about that later on. We are also given the mechanical efficiency of 70%. All right. Specific heat capacity of the exhaust gases. All right. This one, let us just write it here. It's not a problem. Mechanical efficiency, 70%. Then they are talking about the exhaust gases. All right. This is about the exhaust gases. This one. The specific heat capacity of exhaust gases, that is CP for the exhaust gases, 1.05 kilojoules per kilogram Kelvin. All right, that's for the exhaust gases there. Then the exhaust temperature rise, the temperature rise for the exhaust, just like what we had for water, there was a temperature rise for water. This one is for the exhaust for 27 degrees Celsius. There's a lot of information here. The specific heat capacity for cooling water. This is for cooling water, 4,1. This, remember, for cooling water here. So we've got the specific heat capacity for water. This is for cooling water there. So that is 4,187 kilojoules per watt per kilogram Kelvin. That's what we have. Okay. Good information, good information. Let's see. It's a lot of information, I know, but you are supposed to get used to this. This is N6. This is no longer N5. So we are supposed to get used to something of this. It's not that much. It's not that much. All right. So let us check our questions now. With this information, what are we given? The first question was to calculate the brake power in kilowatts. The brake power in kilowatts. Given that it's a rope brake that we have. So meaning to say to calculate brake power, it's easier as we know the formula. We know the formula, it's a rope brake, guys. It's a rope brake that we are given. So we know this and we talked about this. So from our 2 pi Tn over 60, we can calculate this. So remember, this formula is 2 pi Tn or Nt over 60 is one and the same thing, where this is our torque. But we do not, or we are not given the torque in this case. We are given the radius and the mass. Remember that the torque is equivalent to the force times the radius, where force is mass times what? The gravitational acceleration. So we've got mass times gravitational acceleration times what? Times the radius. All right, so that's we're going to have the torque in this case. The mass, which is 40. All right, let us substitute here the mass. That's 40 times 9,81 for the gravitational acceleration. The radius in meters, remember we got this from the diameter that we're given, diameter over 2. So we got this as 0,724, or you can just write the diameter as it was, over 2. So this is going to give us something like 284, 0976 Newton meter. All right, you can round off to 3 decimal places, which is fine. But as for this one, guys, this is the exact value that we have as it is. So you can just take it as it is, or you can fix our calculator to 3 decimal places if you want. All right, but as for me, guys, as for this one, I'm going to take it as it is like this. So that means at the end of the day, we're going to have our brake power from this formula. This brake power that we are seeing here will be measured in watts. It is us, we're supposed to convert it to kilowatts. But as we get it direct like this, it is going to be in watts. So it's 2 pi times the given torque in this case, which is 284,0976 times n, the speed, n in revolutions per minute as it is given here, that is 350 over 60. So like I said, once you use it like this, it means your answer is going to be in watts. So to convert to kilowatts, what do? You multiply by 10 to the exponent of -3. Your answer automatically is going to be in kilowatts. So this gives us what? The brake power. So that was the question then. That was the question. So therefore, our brake power in kilowatts is going to be 10,413 to 3 decimal places, which is in kilowatts. And like I mentioned before, kilowatts means kilojoule per second. That is the kilojoule per second. So we have the brake power there. We might need this value for the brake power. We might need this value. Let us just write it aside. Remember, our brake power is 10,413 kilowatt. Okay, so just like that. Just like that. So these are the questions that should be given, and they need you to understand how to apply these formulas, just like this. All right, let's check another question. The indicated power in kilowatts. We are not given the indicated mean pressure, the effective mean pressure. We are not given that. If we were given that, we're going to think about the formula plan or the plus. But we do not have that. So what are we going to do? The only thing that we have to think of if we are not given is the efficient, the mechanical efficiency. Do we have the mechanical efficiency? Yes, we do. Why are we thinking about the mechanical efficiency? Because we know that it carries both the brake power and the indicated power. It carries both. It carries both. Remember our formula. The mechanical efficiency is equivalent to the brake power over the indicated power, output over the input power. The output power over the input power. Over input power times 100%, which is the brake power to the indicated power. So by this, we can find the indicated power because it is the one that we need, and it is needed in what? In kilowatts. So it means we're going to use this in kilowatts. Remember, our mechanical efficiency, 0,7 we divide by 100 is equal to the brake power already given, 10,413 in kilowatts. So if this is in kilowatts, it means our indicated power is going to be in kilowatts. So how are we going to find the indicated power? So that's you and your calculator here. You're going to cross multiply, then divide by 0,7. So that's 0,7 times IP is equal to 10,413 kilowatts. So if we divide by this, 0,7, this is indicated power, this one. So if we divide by 0,7, we are remaining with what? With the indicated power in kilowatts. Since we used the brake power in kilowatts, our answer is going to be in. We're just dividing by a constant there. It's just a number. So that will be 14,876. which is in what? In kilowatts. Just like that. So we have the indicated power there. All right. So we might need this value. Let us just write it aside. 14,876 kilowatts. So there we've got the indicated power. The indicated power. Okay. Let's see. Different questions to answer here. Let us check another part. Calculate the heat on this part, number 3. They are saying, calculate the heat available in fuel, which is Q, in kilojoules per minute. That is where I say the units are very, very important, provided the information that you're given. They need the heat, yes, absorbed, or the heat that is available, sorry, in fuel, which is our fuel power. But since they need this in kilojoules per minute, what does it mean? Okay, let us go back. Talked about this. We have got the mass of fuel here. Remember, I was talking about this mass of fuel. As we understand that the fuel power is supposed to be the mass of fuel per unit time times the heat value, which is our calorific value, which is the one that is supposed to be in kilojoules per watt, per kilogram. But in order for us, because they need this in kilojoules per minute, per minute. That means the mass of fuel must be mass of fuel per minute also. Guys, you need to know your units. It must be kilograms per minute so that we have our answer in kilojoules per minute. So the moment we do this, our answer automatically is going to be in kilojoules per minute. So that's it. Let us substitute and see the mass of fuel per minute, like I did here. I already calculated. If you want, you're going to use 1/20, or you can use the decimal, which is 0.05 kilograms per minute times the calorific value in kilojoules per kilogram, which is our calorific value. We had it somewhere, but we listed this. I still remember we listed this. It's on top. Yeah, this one. Our calorific value, 44,600. So this is going to be 44,600. So by doing this, we are having our answer in kilojoules per minute. That was the idea then. So this is going to give us 2,230, which is kilojoules per watt per minute. So the fuel power is the Q in. This is the heat in, the one that is entering. So we have the fuel power here, 2,230 kilojoules per minute. Fuel power. All right, let's move on. Let's move on. Another question, that is question 4. Calculate the heat absorbed by the brake power. Brake power in, again, take note the units there. Guys, you must be careful. All right. Are we not having the brake power? We have the brake power. Why are they saying the heat absorbed? Because it is given in the different unit, because this is heat, energy, power. It's energy. Already the brake power is there. We already have the brake power there. The brake power is already given as 10,413 kilowatts. It's energy, this one. But what does the kilowatt mean? I talked about this. The kilowatt means kilojoule per second, per second. Remember from our engineering science N3. Kilojoule per second from our science 2. We talked about these units. So how do we convert to the kilojoule per minute as they want this? We simply have to multiply by 60. Remember, 1 minute is equivalent to 1 second. I mean, 1 minute is equivalent to 60 seconds. So the moment we want 1 second, it will be 1 over 160. So we're supposed to divide by 1 over 160. To divide by 1 over 60 like this, to divide by 1 over 60 like this, is to multiply by 60. That is what it means. It is simply to multiply by 60. Take note about that. It is simply to multiply by what? By 60. So this is to convert to kilojoules per minute, because kilowatt means kilojoules per second. So it was a direct question, this one. So that was going to give us 624.78 kilojoules per minute. Why are they asking us like this? It is because of the heat balance sheet. So in most cases, since you have already calculated the break power like this, they are not going to ask this type of a question. No, they're not going to do that. They will just ask you draw or justify the remainder of the heat. It is you who is supposed to know how to convert the units. This is just a unit of conversion that we are simply having. The same break power that we had, but in kilojoules per minute, it is 624.780 kilojoules per watt per minute. We're not supposed to be asked this. No. You are supposed to know this, that when the table is given, let's check the question. You'll see that. If you check here, oh, you are going to see that later on. But if you check on number 8, when they are saying draw the heat balance, they are saying in what? Kilojoules per minute. That is why they are forcing us to calculate this in kilojoules per minute. It is because of that. But like I said, whether they said it here or not, the moment that they say draw a heat balance sheet in kilojoules per minute, guys, you are limited. Whether you answer they were in kilojoules per hour, you have to change them to the unit that you are given there. You have to change them. But here, lucky enough, they gave us stage by stage, kilojoule per this, stage by stage. So already, our answers are in kilojoules per minute. Even on the friction power, the heat lost to friction in kilojoules, because already they want us to have this. All right. But anyways, how do we calculate the friction power? Remember, I talked about the friction power from when we were introducing this class, and I said it is taken from the indicated power. The indicated power, it is comprised of the brake power and the friction power. And I said we can make the friction power the subject. If you still remember our formula, we ended up with a formula like this. All right, so this is 5. We ended up with a formula like this. All right, let me just use this one. Friction power is equivalent to, that is the friction power is equivalent to, so it is going to be the difference that we have, which is the indicated power minus the brake power. But since they need this in kilojoules per minute, what does it mean? It means our indicated power must be in kilojoules per minute. Guys, we saw that conversion which took place here, on the brake power. We changed it to kilojoules per minute. How so? By multiplying by 60, because we said the kilowatt means kilojoule per second. If we check, we have got indicated power here in kilowatt. And I said the kilowatt means kilojoule per second. So meaning to say, in order for us to have our indicated power in kilojoule per minute, it is going to be the kilojoule per second, which is 14.876 times 60. The same way we converted this one. It was the same. Isn't it the kilowatt? It is the same kilowatt. Only that this was for brake power. It does not change because it is now for the indicated power. No. It does not change. It does not change. Minus the brake power. The brake power is given in kilojoule. We are not going to use this because this one is kilojoule per second, kilowatt. So we are going to simply use this one already that we converted to what? to kilojoule per minute. And what is it? 624,780, which is just 78. So we have converted this to kilojoule per minute by multiplying by 60. This was already in kilojoule per minute. Remember, we did the conversion. We did the conversion here. So this is it. So by subtracting this, we are obtaining the friction power in kilojoules per minute. That is the idea there. All right, so this was gonna, if you want to calculate this, 1 is gonna be 892, sorry, 56 minus 62, this is 624, remember? 624,78. So if we subtract, that will be 276,78 in kilojoules per watt per minute. That is our friction power. All right, so we have got the friction power there. Don't confuse the friction power with the fuel power. The fuel power is the supply, guys. But the friction power is the one that is built up, the one that is a build up of what? Of the indicated power with the brake power. The brake power, when added to the fuel, to the friction power, it gives us the indicated power. So you can make the friction power the subject. But the fuel power, it's on its own. It's a different thing. Mass times heat value, remember that. All right, that's it. Let's see. So when it is like this, it's going to be an advantage when you are answering the last question. 6, calculate the heat lost to the coolant to coolant. The coolant, all right. On the coolant, what is it that we have? This is our coolant here. We have got the change in temperature for water, the specific heat capacity of water. The moment we have got the specific heat capacity, it means our Q for the coolant, which is Q water in this case, which is the coolant, is going to be equal to the mass of water, the specific heat capacity of water times the temperature rise, which is the change in temperature. Since this is needed in kilojoules per minute, it means the mass of water is the controlling part. The mass of water is the one that controls. It must be in kilograms per minute also, per minute. But let's check. We are given this per hour. So per minute means what? That will be 300 over 1 hour is equivalent to 60 minutes. So we have to divide by what? By 60. Times the specific heat capacity of water. They are different specific heat capacity. We need the one for water. Times the change in temperature. The change in temperature is our temperature rise for water, which is 11. So this is going to be the heat taken to the coolant. So this is going to give us 230,285 in kilojoules per watt per minute. As I said, that if this is in kilograms per minute, this will be kilojoules per minute. So we have the Q for water, which is for the coolant. All right. So we have got Q for the coolant. All right, I'm just writing this aside because I need to erase, guys. If I use a lot of space, we know this board, it turned up to misbehave, and I end up now losing important values because of the misbehave of these online boards that we are using, guys. These, I mean, Microsoft, are they Microsoft? These boards that we are using, actually. Anyways, let's see. That was to the coolant. Let's check another question. The other part is to the exhaust. The heat lost to exhaust gas in All right, The one for the coolant, sorry, it was not mentioned. But the reason why I am stating the kilojoule per minute is because, take a closer look, guys. We are going to need the heat balance heat in kilojoule per minute. All these are kilojoules per minute. We have to. We have to write our answer in what? Kilojoule per minute. And for us to have maybe kilojoule per hour, then we change it later on. No, we can't do that. Take advantage of the questions that are there later on. The heat balance is needed in kilojoule per minute. So that is why we have to force up this to be written in what? In kilojoule per minute. Because someone might be asking, why are we using per minute? Why can't we just use per hour? Yes, you can do that because you are not given the units there. But for the sake of revision, use something that is of advantage to your question. All right. Calculate the heat lost to exhaust gas in kilojoule per watt per minute again. All right, this is the information about the exhaust here. About the exhaust. All right. So what is the Q to the exhaust? The Q to the exhaust, the same way that we do on calculating the Q for water. But this one, it will be mass. The mass of what? Of the exhaust gases times the specific heat capacity of the exhaust gases times the change in temperature of the exhaust gases. Where is this one taken from? Where is it taken from? All right. Let's talk about this first. The units for this heat is needed in kilojoules per minute. So it means the mass of the exhaust gases must be in what? Kilograms per minute. All right, we have this, is fine. So meaning to say, I want you to be careful because I talked about the air-fuel ratio before. So you might have a confusion now to say, what I'm saying right now and what I said before does not tally. No, it tallies very much. It tallies very much. Understand this. I said before, the mass of the exhaust, it's simply given from the air-fuel ratio. The mass of air plus the mass of fuel from the ratio. But when you are to consider the units or the unit of measurement, that is per minute, per second, it is the mass of fuel which carries the time here. The mass of fuel per minute, per second, per hour. So it means to obtain this, we must multiply by the mass of fuel per watt, per minute. Per minute, because we need this per minute. Not per second, not per hour, no. Where this is our air-fuel ratio. Remember, this is from our air-fuel ratio. Air-fuel ratio, the mass of air to the mass of fuel, that is what it means. The mass of air to the mass of what? To the mass of fuel. What is the mass of air? 25. What is the mass of fuel according to this? It's 1 times the mass of what? Of fuel per minute. So that we obtain this per minute also. So the mass of fuel per minute is given, we have it. The mass of fuel per minute, 1/20 or 0.05 kilograms per watt per minute. So this is up to you. So this gives us the mass of the exhaust gases as a kilogram per minute. You are going to obtain 1.3 kilogram per minute. Guys, if we use this value, definitely our answer for this Q for the exhaust will be in kilojoules per minute, because we used kilograms per minute. So that will be 1.3 times the specific heat capacity of the exhaust gases we are given there, 1.05 times the change in temperature for the exhaust. They rise there it was 427 degrees Celsius. So that's it. We are going to obtain 582,855. This is 8,855 in kilojoules per minute, as I said before, that this is kilograms per minute. So this will be kilojoules per minute. But also here, it plays a role. How to find the mass of the exhaust gases, it plays a role. All right? So we have got a Q for the exhaust gases, which we got as 5, not 5, this is 582,855, which is kilojoules per minute. All right, so that was our question. That is everything there. Then they are saying, draw up a heat balance. This is what we need here. Okay. We need to draw up a heat balance sheet in kilojoules per minute and express all values as percentages of heat supplied per minute. Per minute. All right, I talked about this on our heat balance sheet. I just hope, guys, you still remember all the heat that is needed, everything that is needed. And I'm just going to remove some of the information that is necessary, that is not necessary, so that our board does not drag. Because as I'm seeing here, finding my board dragging so much. Are you going to need this? No. We used all this. All right, anyways, no problem. These are the heats, all the heat that we have, the heat, this, brake power. Remember, we are not going to consider the indicated power, because the indicated power, it is the one that consists of the brake power and the friction power. I explained that one. And also the diagram. I explained this, guys. Let us just have this. So I said we are going to have Q in. All right, so you're going to have Q in, which is the heat from fuel. Fuel. All right, then Q out. So this is our Q in actual sense. This is our Q in. Then we have got Q out. So Q out, this is heat 2. All right, which is also the units. We are told this must be in kilojoules per minute. Kilojoules per minute. Kilojoules per minute also here. Kilojoules per minute. So that is what we have. So if we check here, everything was already in kilojoules per minute there. So we're not going to worry much. And this is the percentage heat supplied. All right, so let us see. So what is it that we have? The heat from the fuel. This is our input, which is our fuel power. So there we are referring to the fuel power, the input, the fuel power. Is the fuel power in the units that we are given already. We calculated our fuel power and it was exactly in the units. This one, it's kilojoules per minute already. It's in kilojoules per minute. That's our fuel power. All right. It's already in what? Kilojoules. This one, kilojoules per minute. So this is equivalent to 2,237. Already it's in kilojoules per minute. Then Q out. Remember, we said we are going to need the brake power and the friction power together, which give us the indicated power. So here we are talking about what? The friction power. So are they in kilojoules? Yes, the brake power, we changed this. You remember, there was that question that forced us to change this. It is kilojoules per minute already. So on this one, this is where I was saying, if you had no question like that, then now you have to change it. That is where you have to multiply by 60, but already we changed that. So this is 624,780, all right, in kilojoules per minute. The friction power, we already have this 267.78, which is kilojoules per minute. Already it's in kilojoules per minute. Then we saw that we're going to have the heat to the coolant, to the exhaust, and the remainder. Those are the last, the exhaust and the remainder. All right, sorry for that. So we're going to have the one to the remainder by difference. So remember, our remainder is by difference. And we calculated all these, the coolant, Q to the coolant in kilojoules per already is there. 230,285 in kilojoules per minute. To the exhaust, we also calculated to the exhaust in the same units. It's already there. 582,855. So that is it. So this is by difference. So what you do is that you take your fuel power, because your fuel power is the total. All right. So you're going to take this total from our fuel power. Very sorry for this, guys. All right. Let's just hope it's going to be clear. All right. So from the fuel power, you take that as a total. This, which is 2,230. This is 2,200 and what? 230 in kilojoules per minute. So we are going to subtract all these from this. That is our remainder. So it's 2,230 like this. We subtract everything. We subtract our brake power. All right, we subtract our brake power, which is 624,78 plus the friction power. So we are subtracting everything. 267,78 plus we subtract this 230,285 plus we subtract also this, which is 582,855. So this is going to give us the remainder by difference. That's our remainder. And that was going to be something like 528, if I'm not mistaken, 524, sorry. 524,297. All right, let's just calculate and see what you're obtaining, guys. Let me know. You see, I'm working with a lot of values, guys. So these common mistakes, they can do happen. So let's also be together to correct if there is any part that you're seeing that here the value is not correct. It's an error that actually happened. Let me know about that so that it can help others also. Then also here you are going to need the percentages, as we know that our percentages is the one that you're given, the brake power to the total. So if you need the percentage for the brake power, it's going to be the brake power 624,78 over the total, which is our fuel power, 2230 times what? 100%. So you're going to do like this, 100 times 100%, you round off. So I'm just going to round off these to three decimal places, all of them. So this will be 28,017%. That's as a percentage. You do the same thing. The friction power over the total power times 100%. You are going to get 12,008. The same thing on the coolant. The one that we have on the coolant to the friction power, the total times 100%. So that is going to give us 10,327. The same thing for the exhaust. The exhaust, what we have, the total to the fuel power times 100%. That is for the exhaust, which is going to be 26,137%. The remainder, again, over the total times 100%. So our remainder was going to be 23.511%. So if we add this properly, you are going to obtain 100%. So in some cases, like I say, the friction power is not considered. They tell you a condition for that, and you work with the condition that you're given. All right. You use the condition that you are given there. What you are given there is what you use. What are you given? That is what you use. So these are the typical questions that you might be given. So you just have to work on more questions. But for now, that's it, guys. From Mason African Motives, till we meet again.